All right, so grid world, pretty simple, right? Like, you know, you've got your state as which grid you're on, and that's kind of pretty straightforward. You've got a number of states, and yeah, you can build a Q table. Now, often sensor readings are not going to be as easy as 5, 4. You're going to have continuous variables involved, and so how do we deal with that? We're going to start using it, moving forward to a Cartpole environment and see what sort of observations we receive in this environment, and we're going to look at how we can potentially deal with that. So to explain, the Cartpole environment is, as the name suggests, it's a pole on a cart. The objective is, you know, it's susceptible to gravity, so you do not think the pole is going to collapse at some point. The objective is move the cart to try and maintain the pole upright. If the pole falls 12 degrees or to the left or right, it's a fail, episode ends. This environment is also interesting in that every time step you get a reward of 1. Even if you've fallen over. And also, if you've gone too far to the left or too far to the right, it's also a failure. The objective is to keep it up for 200 time steps, and that's when the environment is going to say, yeah, I'm done, you've solved it. So, what the environment gives you from an observation space is actually different to what we've seen so far. There's 4 readings. One is the position of the cart, which can go from anywhere to minus 2.4 to 2.4. And cart velocity, how far is it moving left or right? It actually says infinity, right? In reality, it will probably terminate by then. There's also the pole angle. That's the extreme, but really it already fails when it's about 12 degrees left or right. But the challenge is, how the hell do we put this into our table? Any questions? Any takers?
Quantization.
Sorry, say it again?
Quantization. Quantization.
Containerization or?
Quantization.
Quantization, right, yep. So the idea is, even though we're getting readings back that are continuous, we're going to put it into buckets or bins and work with that as our state space. So let's say if we define our bins, you know, between 0 and 4, we want to have a discrete set of states, and we've specified that we want about, I would say this is about 6 bins, and each boundary is at 0, 1, 2, 3, and 4. Any reading that we get back that's before 0, they'll get a bin number of 0. Any variable between here will get a bin number of 1, and so on and so on. And anything past our boundary will get a bin number of 5. So by specifying 4 barriers, we end up with potentially 6 bins indexed by 0. Yeah? So let's do another exercise, or walk through an exercise. This one you can take home and do because it's a little bit finicky and requires quite a bit of exploration, but it's quite fun to do, I think. Simply because I find it interesting because now we're working with, now we're trying to build an agent who has absolutely no idea what all of this means. We don't really care about the physics. It's just going to play around using the reward, and eventually it's going to learn to prop the stick up without understanding any of the physics involved. Now, if you instill human knowledge into your code, you can probably solve it really easy because, you know, just do a left right depending on whatever calculation you have, right? But what we're trying to achieve here is actually trying to achieve the same objective without understanding the state space. And also, the value in there is also we're creating an algorithm that can solve problems that are more than this specific one. If you're trying to solve based on physics, then the algorithm only caters for this specific scenario. So homework. I'm gonna walk through what you're gonna do, and also I will share with you the link as well. So I'll give you a few minutes to open it up, and I'll walk through it. I'll also show you what a solution might look like, so you can implement it yourself. And then I'll quickly just do a wrap up of today's session after that. Okay, so I've provided a link here, so if you want to read and understand the environment a bit more, feel free to open it up. It explains it a little bit more. But other than that, the actions are 0 for pushing a cart to the left and 1 for pushing a cart to the right. In some ways, you don't really care because you're going to try a few things and you end up with the optimal solution, right? As per normal, some commands to install a few things and a whole bunch of imports. You can just run them and ignore them for now. This cell is contains some utility functions to actually make it a little bit of a nicer experience, so you can see what actually happens. If you want a video of the environment being run, all you need to do is actually wrap your environment when you create a gym environment, and everything will act as per normal. And in the end, whenever you want to see how it ran, just call show video. So let's see what happens when we do a random walk with our environment, right? So this is the starting state. It's some gibberish of numbers, and every subsequent state gives you a reward of 1, and it's not a terminal state until you get to the end. And here's a video of it, starting off and quickly falling over in a sort of a permanent loop. That's why it looks a bit spastic. If you don't like this, feel free to comment out the autoplay in here. I just can't be bothered to click and play as I walk through this. This cell is about getting a view of our action space for the environment, the observation space, what are the high values for each of the 4 readings that we're going to get. It's ridiculously large, and then there's the minimum values there. And I've got some code here for you to explore what it means to create bins and discretize or quantize variables. So for example, let's say our reading is these sort of numbers, and we want to place them in bins ranging from 0 to 5, and we want, say, 3 bins. Actually, let's do 5. Oh, what happened there? So it's quite, the way np.linspace works is a little bit tricky, so you might want to figure out how this works. So when you say specify 0 to 5 and it's 5 variables, you're actually getting 5 variables here. So maybe what we want is 4 instead. Nope, 6, because of 0 involved. So if this was our bins and our values are that, you can simply say numpy.digitize, pass in your values or readings, and you give bins that you want to split them into. And you can see that a -1 will fit in the 0 bin, a 0.1 because it's between this and that, the 0 bin and the first bin, it's bin 1. 2.4 being between here, it becomes 3, and so on and so on. Feel free to play around this code, understand what the code's doing. But essentially the idea is you take a continuous variable and make it simple and discrete. Again, same thing. I've put epsilon here if you want to use it. I'm going to have to run it so I can show it later. Also, the solution Q table is blatantly here. Feel free to use it as well if you want to use that. And here's the exercise. Now, this is pretty much one step beyond what you just tried to do, which is the grid world. It's going to be the same logic. The only additional thing is you're going to have to figure out how to convert your states into discrete bins for your Q table.
I guess my question was the states. Will the state be toppled between all the variables, or is the combination between all the variables?
You probably don't want to be doing calculations or adding them as your state. You want to treat them as uniquely different numbers, right? So in this scenario, you're gonna end up with there's 4 readings, which means your tuple is gonna have 4 bins, one for each of the reading. Does that make sense?
You mean all the combinations?
Yes. Yes. So for example, because there are 4 readings, if you decide to do 5 bins per reading, you're going to end up with, so when you do 5 bins, I think it ends up being 6 potential bins. So you're going to end up with 6 times 6 times 6 times 6 as all your combinations of states. I don't know what that ends up at, but you might need a lot of epsilon for a long time to potentially explore that sufficiently. This is a really good exercise because then you start to appreciate state space and exploration, and also you get to experiment and try different things to see what works and what doesn't. I look at the potential solution so you get an idea of what it might look like. I would suggest you start plotting how well your training is actually doing. So one training round might, I'm training for 500 episodes here. One training round might look like this. And you can see that after 250 episodes, it pretty much flatlines. It knows what the best thing is and constantly achieves that. What alpha you set at is going to have an impact. What gamma you set at is going to have an impact. How you decrease epsilon is going to have an impact. Your state space is going to have an impact. Play around. So if you have solved it, it might look something like this when you actually run it. And that just goes on forever. But let's see what happens if we just run it for 50 episodes, right? Well, it learns nothing. And it just does that spastic fall over it. I actually also, in the solutions I will share, there's actually one way if you look at the environment and go, hey, the reward doesn't make sense, and I'm going to adjust how the environment does the reward, you can potentially achieve something really quick, and I'll leave that up to you to figure out. In this scenario, within about 25 episodes, it already knows what the best action is. That's for you to explore and try. Yeah? Okay, so feel free to ask questions on the forums. I'll be happy to answer any questions. But from today's perspective, I hope you take away an understanding of Q learning, how Q learning is temporal difference learning, just by updating estimates by looking at one time step ahead. And you appreciate how the value actually propagates back as you, in a sense, brute force your experience with the environment. And it is a learning algorithm that's based on experience. Definitely the challenges with Tabular Q is certainly your state space, right? And sufficient exploration. For example, if we were to take an image of the Cartpole and try to apply this algorithm, we're screwed. Or if you're trying to apply an Atari game using this same algorithm, even if you just have 200 times 300 pixels with RGB, you're going to be a bit screwed trying to put that into a state space. And also, by putting things into bins, we are specifically telling our algorithm, even though this state is right next to this state, we are distinctly not or we are not drawing any relationships there. They are distinct states. And this is where next week you'll get to see how we might overcome some of these challenges. But please do the exercises, because an appreciation for tabular Q and understanding that, I think, is really important to go to deep Q learning. That's where you can actually take in an image and beat an Atari game or play it better than a human. Alex Long next week will show you how that might work. We'll apply it to the Cartpole scenario using readings and not images, because images will take you a long time to train, but Cartpole is a really nice environment for us to test algorithms. All right, thank you very much, everyone. Feel free to stay if you want to ask some questions, but I don't think we have too much time left because we've taken a long time today.
Yeah, feel free to stay till 9 if you want to carry on working together in your groups.